Welcome, dear listeners. Now, I want to take you back to 17th century England, to a time when the wind struck stone walls and the fields were veiled in morning mist. The year is 1642. The echoes of religious war still reverberate across the European continent, while the sky over England is darkened by the smoke of civil war. The conflict between King Charles and Parliament has split the country in two, and the land trembles in silent chaos. Yet, amidst this turmoil in the rural region of Lincolnshire, in a tiny, unnoticed village called Woolsthorpe by Coast, a baby is about to be born. No one has ever heard of this village, and no one knows that the child born there will one day change the course of human thought. At that time, Woolsthorpe consisted of a few stone houses, a few acres of farmland, and quiet roads filled with the howling of winter winds. Farmers went to fields early in the morning, women spun wool, and in the evening, the village was filled only with smoke rising from chimneys and the occasional bark of a dog. But in December of 1642, in this quiet village, a birth began. Inside a small stone house, on a snow-covered night, the wind seeped through the cracks in the windows, and a young woman teetered between life and death. Her name was Hannah Ayscough Newton. The baby in her womb had lost his father months before birth. With fear and isolation, Hannah prepared for delivery. On the night of December 25th, 1642, by the calendar then in use, a frail, tiny, almost translucent baby came into the world. He was so delicate that villagers believed he would not survive until morning. As small as an apple, they said. Some whispered. He could fit into a 1-liter jar. Yet he survived. He breathed. With a quiet whimper, he clung to life. Who could have known that this fragile breath would one day speak the laws of the universe? This child would grow to explain gravity, the laws of motion, and the nature of light. Isaac Newton. Newton's father, Isaac Newton Sr., was a respected farmer in the village. Not wealthy, yet not poor, he owned around 100 acres of land. Fate, however, did not allow him to witness his son's birth. He had passed away 3 months before Isaac was born. Thus, little Isaac entered the world fatherless. For his mother, Hannah, it was a devastating blow. A young woman in her 20s, she was left to raise a child alone. But fate had yet another turn. Before Newton even reached the age of 3, he would face another upheaval. Hannah sought security for both herself and Isaac, so she remarried a wealthy clergyman, Barnabas Smith. Yet this marriage brought hardship for young Isaac. His stepfather did not want him. Smith refused to take another man's child into his home and told Hannah, "Leave him. There is no place for him in our new life." Desperate, Hannah left Isaac in the care of his grandmother in Woolsthorpe and moved with her new husband. Isaac was just 3 years old. This separation left a deep wound in the child's heart. Years later, Newton's notes reveal his lingering resentment, anger, and longing toward his mother. Some historians trace the origin of Newton's later reserved, distant, and emotionally guarded personality to this childhood trauma. He grew up in the absence of love, with a closed emotional world, rarely approaching others. Perhaps this solitude turned his mind toward another direction, the silent order of nature. When he could not understand people's emotions, he turned to understanding the laws of the universe. Growing up with his grandmother, Newton's childhood unfolded across the wide fields of Woolsthorpe. He awoke to the calls of cows in the morning, and in the evenings by the light of a small candle, he scribbled in his notebook. While other children played, he sometimes just watched the sky, observing the movement of clouds, the flapping of birds' wings, the direction of the wind. Perhaps unknowingly, these impressions were the seeds of his future great ideas. Everything was an observation. The flow of water, the fall of a stone, the stretching of a shadow. The Newton family was of modest means but respectable. They were not noble, yet they had standing in the village. With small ancestral lands and a few animals, they made their living. Social class distinctions were pronounced in England at that time, and Newton had no connection with the nobility. When he entered the world of science, he was long overlooked by those of noble birth. Yet, his intellect would quickly overcome these barriers. At the time of Newton's birth, England was engulfed in civil war. The country was divided. Supporters of King Charles I on one side, parliamentarians on the other. Villages, cities, even families were split. Religious disputes, political conflicts, fear, and uncertainty prevailed everywhere. Hannah Ayscough Newton was devout and instilled in her son a reverence for God and the practice of prayer. This religious discipline left a deep mark on Newton's mind. Throughout his life, he believed in God, seeing the laws of the universe as reflections of divine order. Yet, he never abandoned scientific skepticism. Faith and science were inseparable for him. He believed the truest understanding of God's creation came through science. As the years went by, Newton's character became more defined. Reserved, meticulous, quiet, yet possessing extraordinary powers of observation. He built small mechanical toys and windmills as a child. His family considered his curiosity peculiar. But in reality, Newton was a natural-born investigator. The quiet of the countryside shielded his mind from noise and deepened his thoughts. Thus, in the heart of England, under the shadow of war and uncertainty, in a small stone house, a miracle grew unnoticed. Fatherless, separated from his mother, nurtured in the village's silence, this child would one day decode the structure of the universe and write the secrets of the sky in the language of mathematics. His life began on a dark winter night. Yet from that darkness, he would bring forth the law of light. Isaac Newton's story began like this. In a rural village, with a single breath between life and death, a breath so powerful it would change the journey of human knowledge forever. Isaac Newton's childhood is like a painting where light and shadow intertwine. The quiet years spent in the stone houses of Woolsthorpe shaped his spirit profoundly. Growing up fatherless and separated from his mother at an early age, this small child learned to listen to the world in silence. Where words among people lost meaning, he attuned himself to the voice of nature, the whisper of the wind, the rhythm of the rain, the apple falling to the ground. These early years carried in his mind the first sparks of ideas that would later crystallize into formulas. When he was 3, his mother moved to another village, leaving Isaac with his grandmother. For a small child, this was not just a separation, it was a collapse of a world. With his mother gone, a profound silence took root within him, a silence that would accompany him throughout his life. Newton never became a talkative person. He neither shared his feelings nor easily revealed his inner thoughts. He appeared distant, sometimes even cold. Yet behind this outer stillness, a storm brewed in his inner world. His thoughts, observations, calculations, all grew within the silence. Village life was simple but harsh. Isaac watched people working in the field in the mornings and helped his grandmother with farm tasks. Yet he never truly embraced agricultural labor. He preferred to move his hands over a notebook rather than the soil, to hold a pen rather than a plow. One day, his grandmother found him in a corner of the kitchen, drawing in an old notebook. Isaac was trying to recreate the village mill. Small sticks, strings, and stones. He put them together so that when the wind blew, the mill would turn. Even as a child, he was learning not just to imitate nature, but to understand it. Newton's introverted nature set him apart from other children. Rather than playing with friends, he examined objects and built mechanical devices. According to legend, as a child, he amazed other village children with a small windmill he had made. The mill turned with the wind. The gears moved in a precise sequence, and a tiny stone wheel created a mechanical sound. For a child of his age, this was extraordinary. But this was Isaac's world. Motion, cause, effect. Everything had a reason, and that reason could be discovered. Years later, when his mother became a widow again, she decided to return to Isaac. By then, he was 9 years old. Yet the distance between them was not easily bridged. Newton had grown estranged from his mother. He remained at the age when he had lost her love. Shortly afterward, his mother tried to involve him in farm work. Newton's tasks were to inspect the fields and take produce to the market. But these duties were torment for him. On one occasion, she sent him to the market. Isaac set off with a cart, But instead of reaching the market, he sat under a tree and began reading a book. Hours later, he returned home having forgotten half the goods. From that day, his mother realized he was not suited for farming. Newton's mind was elsewhere, in the sky and light, in numbers. During these years, his inner world slowly took shape. Newton recorded his observations in notebooks, documenting his own small inventions. By candlelight, he experimented with little devices he had built himself, bending the direction of light with pieces of glass. Even before formal scientific training, he had laid the foundations of experimental thinking on his own. He did not merely watch nature. It was as if he conversed with it. He wondered why a raindrop rolled, how shadows changed, how the world operated. Yet alongside his curiosity, a dark side grew within him. Newton transformed the loneliness of his childhood into a protective wall. He did not easily trust others. From an early age, he harbored a sense of quiet competitiveness. When he taught someone something, he was unsettled if they could surpass him. This would form the psychological groundwork for the disputes he later had with scientists like Hooke and Leibniz. But at the time, no one saw that beneath these deep emotional struggles lay the future's greatest genius. One of the pivotal moments of his childhood was being sent to school. His mother enrolled him in a school in the town of Grantham. This was his first departure from Woolsthorpe. The town appeared immense to his eyes. During his stay, he lodged with a local apothecary family. It is said he formed a small friendship with the apothecary's daughter, yet Newton's attention was focused on books. The town library was a treasure trove for him. Geometry, astronomy, poetry, the Bible, he read whatever he could find. By candlelight, he would make notes in the margins, adding his own observations. His years in Grantham opened Newton's inner world. He stepped out from a countryside into a larger environment. Yet he was not one to blend in easily. While other students talked, he quietly scribbled in his notebook. While the teacher lectured, he was lost in thought. Many called him a dreamy child. Yet his teachers soon realized that his daydreaming was a form of profound attention. Newton's mind was several steps ahead of the others. He solved arithmetic problems instantly and surpassed everyone in logic exercises. Yet even these achievements could not erase his sense of loneliness. Newton felt closer to ideas and to people. Those around him found his introversion strange. But for Newton, it was a form of protection. Staying away from the emotional chaos of humans was his way to keep his mind clear. He sought to understand the world not through feelings, but through laws. Over time, this habit became permanent. Newton remained genuinely close to very few people throughout his life. He did not write down his emotions, but some lines in his notebooks reveal the depth of his inner world. On one occasion, he wrote, "The human heart is the most complex order in nature, yet it cannot be observed." Perhaps this is why he turned to unraveling the laws of nature. Unlike humans, nature had consistency. As he entered adolescence, Newton's mind was far more advanced than that of an ordinary student. By the age of 16, he was already engaged in algebra and geometry. Even when he returned to his village, he did not work in the fields. Instead, he sat atop a stone wall watching the sky. His neighbors thought him mad, yet he was witnessing the order of a universe. He believed everything had a law, and he patiently observed to understand it. Thus passed Newton's childhood and youth, in silence, observation, and solitude. But that solitude did not break him. It shaped him. Every abandonment, every quiet day, every forgotten supper placed a stone in his character. Those stones would one day become one of the strongest structures in science. Isaac Newton, even as a child, began to hear the language of a universe. And that language whispered into his mind, "Everything has a reason." This sentence would become the deepest truth of his life. A cold morning, the wind whistles through the stone houses of Grantham. Isaac Newton, only 12 years old, slung a small bag over his shoulder and set out from Woolsthorpe. Bare trees lined the road, and distant hills were shrouded in the morning mist. This was his first departure from the world he knew. leaving the farm, the sound of animals, and his mother's pressure behind, yet unknowingly walking toward his own destiny. That morning, Isaac took his first step into the silent lands of science. Grantham was a small but lively town. The narrow streets echoed with the wheels of horse-drawn carts, and merchants shouted their wares in the market square. Amid this crowd, a quiet, introverted boy seemed to observe from another realm. Newton's face was always somewhat serious, his gaze distant. Even at that age, he lived not in the world of other children, but within himself. The King's School in Grantham marked the beginning of his formal education. Its stone walls and tall windows, with quiet classrooms, resembled a small monastery. Students spoke Latin, memorized passages from the Bible, and learned basic arithmetic. But to Isaac, these were dry facts. His mind wandered beyond the walls, roaming the sky and nature itself. Newton's early months at school were not remarkable. He was quiet, struggled to make friends, and his daydreaming often earned him scolding, sometimes even being labeled lazy. But his absent-mindedness was not from disinterest. It was a form of deep attention. He often stared out the window, studying the movement of clouds. The teachers didn't notice, but Newton made his own notes, observing the shapes of clouds, the speed and direction of the wind. In his mind, everything had an order: the sky, the wind, even time itself. Soon, the headmaster suggested he stay with a family in Grantham, coming from Woolsthorpe. Newton moved into the home of William Clark, the town's respected apothecary. That house would become young Isaac's laboratory, world, and sanctuary. Clark's home was filled with glass bottles, plant extracts, metal scales, and jars of colorful liquids. Newton wandered among them as if mesmerized. In the evenings, he would sit at the corner of Clark's work table, watching his mixtures. Sometimes, secretly, he performed his own small experiments when Clark was away. On one occasion, he mixed vinegar with metal powders and marveled at the smoke that rose. At that moment, he sensed the invisible laws of nature, though he could not yet name them. Clark's daughter, Catherine, was the only one who noticed Newton's quietness. A friendly bond formed between them. Catherine loved reading, and Isaac read with her. Together they would gaze at the sky, counting the stars and learning their names. While the town's children played, they would sit silently in Clark's garden, Newton turning his small wind vane. Catherine said he was strange or intelligent, while the townspeople called him the odd child. Yet in Newton's inner world, a completely different universe was forming, a universe whose language was not words but moving things. Light, shadow, water, wind. Isaac began building small machines in Clark's courtyard. Tiny wooden water wheels, a windmill, even a miniature sundial he made himself. He crafted the sundial so precisely that Clark's customers began telling time by it. Even as a child, he had created a device to measure time, in a sense, attempting to understand it. He calculated the angles of the sun's shadow and made notes. Years later, when he defined time in the Principia as a fundamental measure of motion, perhaps he recalled the intuition gained from making that sundial. Newton didn't just build machines. He observed human behavior too. From Clark's window, he watched the blacksmith across the street, counting the rhythm of hammer strikes. Sometimes, he would attach small pieces of paper to doors to see if the wind's direction had changed. His mind questioned nature through experiment. He did not fear asking questions and sought answers through experimentation. Even at 13, the answer, because God willed it, was not enough. He believed that understanding gods would require deciphering the mechanism of the universe, unknowingly living the essence of scientific thinking. During his years in Grantham, Newton's character also took shape. He was combative, stubborn, yet introverted. One day, a classmate mocked him. Newton withdrew silently, but the next day he was different. From that moment, he worked to surpass his rival. At night, he memorized Latin words and solved mathematical problems by candlelight in Clark's laboratory. Soon he became the best in the class. This marked the birth of the competitive spirit he would carry throughout his life. Even in science, traces of the spirit remained. The disputes he would have with Hooke, Flamsteed, and Leibniz all stemmed from the same spark. Once he felt superior, he would never relinquish that position. Yet these achievements did not diminish his solitude. In Grantham, everyone talked about his strangeness. While other children played, he observed falling shadows in the schoolyard, calculating the sun's movement with his charts. The townspeople would say, "Isaac is scribbling again," unaware that these scribbles were the first lines of mind beginning to describe nature in the language of mathematics. The years at Clark's house gave Newton not only knowledge but a sense of order. His belief that everything was measurable took root during this period. Newton understood that observing alone was not enough to understand nature. Experiment and numbers were essential. He recorded notes, logged observations with dates. These notebooks would form the foundation of the scientific method he would later employ. Measure, observe, repeat. Eventually, someone recognized Newton's talent. Headmaster Henry Stokes. Stokes saw the silent boy's notebooks and drawings and was astonished. "This child was not made for farming," he said. He went to convince Newton's mother, Hannah. She initially resisted, wanting her son to manage the farm. But in the end, she could not withstand Stokes' insistence. Thus, the door to Newton's destiny opened. The path to Cambridge was visible. Yet at that time, Isaac was unaware, looking out the small window of Clark's house. He was likely pondering how clouds moved in the sky. He was a child growing up observing the world around him, unsuccessful with people, yet fluent in the language of nature. The years in Grantham shaped his mind. His love for understanding nature through numbers was born here. Every stone, every shadow, every breeze seemed like an equation, a secret. And one day, leaning over the table in Clark's laboratory, he watched vapor rise in a glass bottle. He murmured to himself, "Everything moves for a reason." Perhaps it was a child's wonder, but also the first whisper of genius about to grasp the fundamental law of the universe. Newton was no longer an ordinary child. In that small stone house of Grantham, one of the greatest scientists in human history was taking shape. And, unknowingly, he had begun to decipher the language of a universe. It was a summer day in 1661. A horse-drawn carriage ascended the silent hills of Woolsthorpe, heading toward Cambridge. Inside was young Isaac Newton, a few books in hand, an old, tattered suitcase by his side. But inside that suitcase were not just belongings. It held the first notes of mind that would change the future of humanity. He was only 18. This young man, stepping quietly into the world, would in a few years discover the laws governing the universe and redefine time and space. But on that day, as he crossed the gates of Cambridge, no one knew this yet. Cambridge University at the time was the intellectual heart of England, yet the knowledge taught there still largely relied on Aristotle's teachings. People believed the heavens were made of perfect circles, and that matter consisted of four elements: earth, water, air, and fire. The ideas of Galileo, Kepler, and Descartes had not yet fully penetrated England's academic walls. In the stone corridors of Cambridge, the shadows of the Middle Ages still lingered, and this darkness would only make Newton's light shine more brightly. Accepted to Trinity College, Newton initially enrolled as a sizar, a student who served wealthier peers in exchange for the right to education. He cleaned classrooms in the mornings, carried meals for professors in the evenings, and in his free time, buried himself in books by candlelight. But for him, this was not shameful. It was opportunity. Silently observing, he thought in his own corner. He did not make friends, did not participate in conversations. Most students found him odd, saying, "Isaac is always alone." Yet he was not lonely. His friends were ideas. Newton quickly grew bored of Cambridge's classical curriculum. He began questioning the Aristotelian philosophy taught by his instructors. For him, these teachings were ornate but incomplete pictures drawn on the surface of the world. True natural laws had to be hidden within an invisible mathematical order. At night, by candlelight, He secretly read forbidden books by thinkers such as René Descartes, Galileo Galilei, Johannes Kepler, and William Oughtred. Descartes' geometry, in particular, opened a new door in his mind. The idea of explaining nature with mathematics resonated deeply with Newton. From that moment on, he decided to understand the universe not through words, but through numbers. Soon, he advanced independently in mathematics, optics, and mechanics. He often pursued his own curiosity rather than attending lessons. His professors occasionally warned him, saying, "Do not create your own theories before learning what the books say." But for Newton, this was impossible. He was speaking directly with nature. His laboratory was a single room, but his mind was as vast as the universe. One day, tired of the definitions in his textbooks, he wrote a sentence in large letters in his notebook. Amicus Plato, amicus Aristoteles, magus amica veritas. Plato is my friend, Aristotle is my friend, but truth is my greatest friend. These words summarize his approach to science. From that day forward, Newton began laying the foundation for one of the most important scientific revolutions in human history. By 1665, England was shaken by a great disaster, the Great Plague of London. The epidemic spread across the country, and Cambridge University temporarily closed. Newton returned to his hometown of Woolsthorpe. But this return was not a step backward for humanity. It was the beginning of a great leap. In the attic of his house, in 2 years of silence, history would later call the Annus Mirabilis, the Year of Wonders. Back in Woolsthorpe, Newton had a few books, a prism, some iron balls, and a handful of ideas. No longer just a student, he was now a self-taught thinker. He converted the attic into a small laboratory. There, he conducted experiments with light, colors, motion, and gravity. It was in these years that 3 great ideas, destined to change humanity's understanding of the world, began to sprout. Calculus, the theory of light and color, and the law of universal gravitation. One day, sitting at his desk, he looked out the window. An apple fell from a tree in the garden. This simple observation was more than it seemed. Newton asked himself, why does the apple fall down and not up? Could the same force keep the moon in orbit? At that moment, an invisible connection was formed between the sky and the earth. Newton first conceived the idea that every object in the universe attracts every other object, though he could not yet prove it. This thought echoed in his mind for years. During the same period, he began experiments on light, discovering the nature of colors. Sunlight passing through a prism was not a single color, but 7 distinct colors. This discovery shattered the belief in the purity of light. Newton wrote in his notes, "Light is the ink with which God has written the universe." He was deciphering the language of nature, light, motion, gravity. Each revealed a different face of divine order. During these 2 years in Woolsthorpe, Newton's mind never rested. Amid the quiet of the farm, some of humanity's greatest equations were born. Later, he would describe this period. In the years I spent alone in the village with my thoughts, I first began to see the secrets of nature. When the plague ended in 1667, Newton returned to Cambridge. He was no longer the shy student he once was. He had his own ideas, laws, and system. Upon seeing Newton's notes, his teacher Isaac Barrow marveled. I have nothing left to teach him. Within a few years, Newton succeeded Barrow and became a professor of mathematics at Cambridge, not yet 30 years old. But he was now at the center of the scientific revolution. His ideas would eventually reach the Royal Society of England, and in 1687, the Philosophiae Naturalis Principia Mathematica, humanity's greatest scientific work, would be born. Yet even then, Newton still pondered the falling apple, the refraction of light, and the mysteries of motion. His Cambridge years were the time when Newton's genius truly formed. In those stone buildings, he learned not only knowledge, but how to read the universe. Each equation, each experiment, each silent night was like a prayer, and from those prayers, the foundations of modern science arose. The year was 1665. England, The plague that shook London and much of the country had brought life to a standstill. In the cities, a silent death ruled, and Cambridge University was temporarily closed. Students and professors returned to their villages, leaving the stone buildings empty. Many saw this quarantine period as lost years. But for Isaac Newton, these years would become one of history's miraculous moments. Far from people, surrounded by silence, Newton withdrew to the small stone house in Woolsthorpe, where his mind was preparing a storm that would give birth to some of history's greatest discoveries. When Newton returned home, he brought with him a few books, notebooks, and simple experimental tools. The house, a modest farmhouse with a dusty attic, would become his laboratory, his palace of thought, and his stage for mathematics. At that time, Newton was far from teachers, books, and academic prestige. His only companion was his curiosity. His silence and solitude transformed his mind into thought and observation into experiments. Newton first began to ponder motion and force. He questioned the old physical theories he had learned at school, realizing Aristotle's understanding of motion was incomplete. For days and hours, he would sit in the garden observing nature. Sitting under the apple tree, he was prompted to think, why does the apple fall to the ground and not upward? This question marked the beginning of a chain of thought that would lead him from simple observation to a universal law. Newton sensed that the apple's fall was not just a surface phenomenon, but that all objects in the universe could be connected by an invisible force. This intuition was the first spark of the law of universal gravitation. There were no mathematical formulas yet, only a concept in his mind, but that concept would later change the foundations of all physics. At the same time, Newton began charting his own path in mathematics. He did not limit himself to the geometry and math he had learned at Cambridge. He set out to create his own methods. He worked on the ideas of infinitesimals and measuring change. His efforts to translate everyday observations into mathematical equations laid the groundwork for modern calculus. During these studies, he worked from early morning until midnight by candlelight, filling pages with notes and testing his own formulas. For him, mathematics was not merely an academic tool. It was a language of the universe. Formulas were the words that revealed nature's silent laws. In his attic laboratory, experiments on optics and light continued. Using simple prisms and glass, he refracted sunlight to separate colors, discovering that light was not a single color, but consisted of 7 distinct colors. These experiments helped him understand the nature of light and develop a systematic scientific method that combined observation with mathematics. Newton saw solving the nature of light not merely as academic curiosity, but as a fundamental way to understand the structure of the universe. During those years, Newton's mind was not limited to experiments. In the silent attic, he also contemplated astronomy and celestial bodies, the moon's motion, planetary orbits, the arrangement of stars, all connected by invisible laws, which he believed could be expressed mathematically. In his notebooks, he sketched the heavens with symbols, attempting to calculate each motion. These mental exercises laid the preliminary groundwork for the formulas that would later explain universal gravitation and planetary motion. In 1666, Newton experienced one of his greatest bursts of creativity. His ideas in mathematics and physics accumulated so intensely that within months he developed multiple fundamental concepts. The first foundations of calculus, theories on the nature of light, and reflections on universal gravitation all emerged during these years. He was opening doors of knowledge that had been closed to humanity with his own hands. Yet these years were not only about scientific production, they strengthened his personal character and inner discipline. He would forget to eat for hours, spending almost no time with friends or family. In the depths of his mind, there was only the pursuit of the universe's secrets. This intense solitude and mental discipline clearly nourished the genius he would become. Though he appeared to retreat from people, he was wholly engaged with nature. His attic laboratory, garden, and the sky were his observation field. By 1667, Newton's annus mirabilis had come to an end. But the knowledge and experimental discoveries he had gained in this short period would completely change the course of scientific history. The seeds of calculus had been sown. Theories of light and color emerged, and the idea of gravitational force had crystallized in his mind. All these efforts prepared him to return to Cambridge, pursue his academic career, assume the Lucasian professorship, and years later, author the Principia Mathematica. The Annus Mirabilis years were not just a scientific miracle for Newton. They marked the beginning of a unique intellectual revolution in human history. The closed university had become an open horizon for him. Silence, distance from people, and quarantine had transformed into an ideal laboratory for a genius. In that small stone house, in the attic, some of humanity's greatest ideas were born, and the secrets of the universe began to unfold in a child's mind. The years 1665 to 1666 are known as Newton's Annus Mirabilis. The closure of Cambridge due to the plague had forced him to retreat to the attic at Woolsthorpe. This silence caused not only a physical but also a mathematical storm to break out in his mind. During these years, Newton felt the need to develop a new tool to understand the concepts of motion and change, calculus, or the method of flux ions. In Newton's eyes, everything in the universe was in constant change. Branches swayed in the wind, apples fell, celestial bodies moved in their orbits. However, existing mathematics could not fully express this continuous change. Geometry and classical arithmetic could only describe fixed shapes and quantities. Newton decided to develop a system in which change could be measured mathematically. Thus was born a language with which he could describe the velocities, accelerations, and paths of moving objects. Calculus. Newton named his method in his own terms the method of flux ions. Flux ions was a concept expressing continuous change. Newton thought of the flow of each variable over time, laying the foundations of the concepts of derivative and integral to measure this change. In other words, Newton's mathematics no longer concerned itself solely with static shapes, but with moving, changing, and evolving systems. In his mind, equations were alive. A point moved, a line changed, a curve continuously evolved. The birth of calculus was not merely a product of Newton's curiosity. It also arose from the need to solve physical problems. Classical geometry was insufficient to explain the law of universal gravitation, the orbits of planets, and equations of motion. Newton had developed a mathematical tool capable of measuring motion and change. And the method of flux ion provided exactly that. With this tool, he could define systematically and precisely the relationship between an object's position, velocity, and acceleration. However, this mathematical revolution also gave rise to a historically significant controversy: the dispute with Gottfried Wilhelm Leibniz. Leibniz, independently from Newton, had developed a similar calculus method in Germany around the same time. Leibniz's notation, particularly for integrals and derivatives, was different from Newton's and appeared more practical. Yet Newton claimed he had developed his method first. The dispute, which began in the 1680s, evolved into an academic conflict between Newton and Leibniz. Even the Royal Society found itself in the middle of this debate. Both sides defended their claim to both mathematical methods and historical priority. Newton's approach was more methodical and closely linked to physical problems, whereas Leibniz's approach was more practical in terms of formulation and notation. Consequently, the mathematical world appeared divided. England followed Newton's method, while continental Europe preferred Leibniz's notation. Yet beyond the disputes, calculus itself completely transformed humanity's capacity to think. It became possible to measure continuous change in fields such as physics, astronomy, engineering, and even economics. Newton's method of flux ions revealed the mathematical dimension of his scientific genius. Discovering a physical law like universal gravitation would have been almost impossible without calculus. Calculating the motion of planets, the fall of an apple, and the acceleration of moving objects would not have been possible without this new mathematical language. Newton had become not only a physicist, but also a mathematical architect, creating his own language to describe the laws of the universe. In summary, Newton's calculus made the mathematical expression of motion and change possible. provided the foundation for formulating universal gravitation and laws of mechanics, became a cornerstone of modern mathematics and the scientific method, and, despite the dispute with Leibniz, created an irreversible revolution for humanity. During this period, Newton's mind in the solitary attic room spoke to the universe through experiments, observations, and his new mathematical language. Every formula, every equation, every calculation was a discovery, every thought a contribution to human history. Calculus, combined with his observations, made Newton not merely a scientist, but a genius who decoded the mathematical order of the universe. 1669. The winds in England blew sharply. In the world of science, the clash between the old and the new was growing stronger. Aristotelian thought was slowly giving way to the dominion of mathematics, observation, and experiment. Amid this era of transformation, within the stone walls of Cambridge University, a young genius was quietly rising, Isaac Newton. He was only 27 years old, and that year, one of Cambridge's most prestigious positions was entrusted to him, the Lucasian Professorship of Mathematics. This position was akin to a throne in the kingdom of English science. The previous holder of the title was Isaac Barrow, Newton's mentor. When Barrow recognized the extraordinary talent of the student, he voluntarily stepped aside, saying, "This chair has now found its rightful owner." It was a gesture rarely seen in history. Barrow regarded Newton's abilities so highly that he did not hesitate for even a moment to relinquish his position. From the outside, Newton still appeared silent, withdrawn, even cold. Yet within his mind, a complex order as intricate as the silent dance of stars was at work. The Lucasian Professorship was not merely an academic title for him. It was a key to a laboratory, a door opening to the infinity of thought. In the dim lecture halls of Cambridge's stone buildings, Newton now conveyed his own ideas. His students listened, spellbound yet slightly bewildered. Newton did not begin with textbooks. He began directly with the universe itself. One day, a student entering his lecture noticed him writing on the blackboard, "To understand nature is to read the mind of God." This phrase captured the essence of Newton's teaching. For him, mathematics was merely a tool, physics was a language, and nature was a sacred text. As a Lucasian professor, Newton focused on two major areas, optics and the laws of motion. At that time, the nature of light was one of the greatest controversies in science. Some argued that light was made of waves. Others claimed it consisted of particles. Newton was determined to resolve this mystery through his own experiments. He filled his home laboratory with colored glass, mirrors, and lenses. For hours at night, he studied sunlight passing through prisms, recording the sequence of colors, their angles, and shadows. Eventually, he proved that what humanity had long considered pure sunlight was actually a combination of various colors. This experiment was so revolutionary that it overturned all previous beliefs about the nature of light. Newton submitted his findings to the Royal Society of England in 1672, yet he sought no applause. Science, for him, was not a personal victory, but a path to truth. Still, his paper caused a great stir among the members of the Royal Society. Some praised him as a new Archimedes unraveling nature's secrets, while others found him arrogant and peculiar. Notably, the famous scientist Robert Hooke criticized Newton's work, and the tension between them evolved into a rivalry lasting years. Hooke advocated the wave theory of light, and found Newton's particle theory inadequate. Faced with these criticisms, Newton withdrew further into himself. After publishing his optical work, he remained nearly silent for almost a decade. Yet even during those years, a storm raged in his mind. Though he seemed indifferent to the world outside academia, Newton was not completely detached from it. He usually held his lectures at early hours for only a few students. Afterwards, he would retreat to his room and work for days without speaking to anyone. Those who observed him recounted that he forgot to eat and would stare for hours into nothingness. Once, a friend brought him food. Newton thanked him, yet did not touch the meal. The next day, The friend returned to find the plate still on the table. "You didn't eat?" the friend asked. Newton replied, "I thought I had." His mind was so deep that it had forgotten the body. During this period, the grand puzzle of the universe began to take shape in Newton's mind. Light, motion, gravity, all were interconnected. Yet he did not dare fully articulate these thoughts. He was cautious by nature. He spoke nothing without proof. But when he did speak, his words became laws of the universe. By the late 1670s, Newton had become a figure spoken of not only in Cambridge, but across Europe. His lectures, a few published works, and circulating rumors had transformed him into a mysterious figure. Many scientists sought correspondence with him, eager to learn his ideas. Yet Newton measured, weighed, and calculated every line he wrote, scrutinizing his words repeatedly to avoid any misinterpretation. On one occasion, he replied to a letter from the Royal Society, "I do not care for dispute. Nature already reveals its truth." This sentence summarized his scientific stance. For Newton, science was not about debates. It was about observation and calculation. The Lucasian professorship granted Newton significant authority at Cambridge. Yet this power only deepened his introversion. Walking through the quiet corridors of the university, students admired him, yet also approached with caution. Some thought him mad. But in the depths of his mind, he was deciphering the mathematics of God. The years following 1669 can be considered Newton's preparatory period. The notes he penned during these years would later form the foundation of his immortal work, Principia Mathematica. Every formula, every observation, every experiment became a brick in the walls of this intellectual edifice. And when that work was finally published in 1687, the world realized Isaac Newton was not merely a scientist. He was a prophet writing the laws of nature. The Lucasian professorship was a symbol of his silent ascent. Many great scientists would hold this title in history, but none would imbue it with the significance that Newton did. For within the stone walls of Cambridge, he did more than lecture. He decoded the language of the universe, expanding the bounds of human intellect. He was no longer just Newton. He had become the mathematician of nature. Between 1665 and 1672, light had become an obsession in Isaac Newton's life. Away from the stone walls of Cambridge, in the dim light of the Woolsthorpe attic, Newton once again listened to nature. But this time his attention had shifted from moving objects to the visible spectrum of light. The white sunlight stood before his mind as a mystery waiting to be unraveled. Every beam was, for Newton, a question, a coded message. The question, "What is light?" was not merely scientific curiosity. It was a quest to understand how God had created the universe. Newton's first experiments were simple, yet they reflected the genius of his intellect. One day, he allowed sunlight into his room and passed it through a prism. His eyes were dazzled. The light was not white, but separated into the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. Newton faced a reality that no one had noticed before. White light was not a single entity, but a combination of different colors. This observation revolutionized his thinking. White light was no longer innocent brightness. It was a mystery of mathematics and physics. Newton did not merely observe the colors. He measured the angles of refraction for each and created a systematic table. He spent hours in front of the prism, carefully recording the sequence of colors, their angles, and the direction of the light. These notebooks became the sacred books of his laboratory. For Newton, the behavior of light was a measurable phenomenon, and each experiment brought him one step closer to uncovering universal laws. He decided to share his findings with the academic world upon returning to Cambridge. In 1672, he sent his first paper to the Royal Society, New Theory About Light and Colors. The paper was brief but striking. Newton proposed that light was composed of particles and that colors arose from the refraction of these particles. This thesis sparked a major debate among the scientific circles of time, particularly because many, including Robert Hooke, argued that light propagated as waves. The dispute between Hooke and Newton will become one of the most famous scientific rivalries in history. Hooke's criticisms did not discourage Newton. On the contrary, they made him more meticulous and methodical. He systematized his observations, repeated experiments, and recorded his findings in detail. During this process, he designed new experiments with mirrors and lenses to explain the behavior of light. He passed the light through one prism and then used a second prism to recombine it, observing that white light reformed. This experiment demonstrated that the colors were not illusions of the eye, but originated from the light itself. After 1672, Newton expanded his work in optics and in 1704 published his monumental work Optics. The book was not merely a scientific text, but a manifesto of Newton's approach to understanding nature. Prism experiments, the particle nature of light, the laws of refraction and reflection, the functioning of lenses and mirrors, everything was compiled in this volume. Newton described his observations and experiments in such detail that the reader felt as if they were in the attic laboratory, witnessing the experiments firsthand. However, Newton's work was not limited to experiments. It was also full of theoretical deductions. By proposing the particle nature of light, he faced scientists advocating the wave theory, leading to long-standing debates. Newton's calm and distant demeanor was evident in these disputes. He did not try to persuade anyone. Nature was his judge, and the results spoke for themselves. Yet, these debates spurred deeper investigations in the field of optics. Newton's studies in optics marked a turning point in the history of science. He systematically proved that white light is composed of a combination of colors. He developed the particle theory of light, explaining its nature through mathematics and experiments. He reinforced the foundations of the modern scientific method, emphasizing experimentation and measurement. The impact of these studies was so profound that centuries after his death, scientists continue to honor his legacy. The prism experiment and the book Optics not only transformed the history of optics, but changed the course of all physics and scientific methodology. The Woolsthorpe attic, the stone buildings of Cambridge, Newton's silent observations, all came together to reveal the secrets of light to humanity. Newton had succeeded in making nature speak, not through words, but through observation, experimentation, and mathematics. Between 1665 and 1667, at Woolsthorpe, while Cambridge University remained closed due to the plague, Isaac Newton had withdrawn into his attic room, immersing himself in his own world. This silence provided the perfect environment for his mind to unravel the most fundamental laws of the universe. Having understood the nature of light through prism experiments, and having measured change through calculus, he was now ready to bring the concepts of motion and gravitation into a mathematical framework. Newton's first step was to define motion. He went beyond classical understanding, rejecting Aristotle's incomplete ideas, such as motion continues only with force. Newton spoke with nature through observation and mathematics. An object moves at a constant velocity when no net force acts upon it. When a net force is applied, it accelerates. This idea would later be systematized as the famous three laws of motion. Objects remain at rest or continue moving at a constant speed unless acted upon by an external force. Newton grasped this law while observing the falling apple and the moon's orbit. Inertia, in his view, was one of nature's fundamental characteristics. The net force applied to an object equals the product of its mass and acceleration. Newton developed this equation to calculate the fall of the apple and the orbits of the planets. Calculus was a critical tool here. Being able to mathematically express change in velocities and positions made his revolutionary work possible. For every action, there is an equal and opposite reaction. Newton used this law to explain not only terrestrial motion, but also celestial movements. The moon's orbit around the Earth, the apple's fall, and even the rotation of planets could all be explained consistently through this law. These laws settled into a universal mathematical framework in Newton's mind. From his perspective, the laws of nature operated the same both on Earth and in the heavens. The difference in force between the moon and an apple was only a matter of magnitude. The mechanism was the same. This insight revolutionized humanity's understanding, unifying celestial and terrestrial motion that had been seen as separate for thousands of years. Newton did not rely solely on observation to confirm universal laws. He used calculus to mathematically prove them. He compared planetary motions with Kepler's laws and realized he could explain both the apple and the moon with the same formula. In that moment, the law of universal gravitation took shape in his mind. Every particle attracts every other particle with a force proportional to its mass. This force is inversely proportional to the square of the distance between them. Newton first tested this law conceptually. The moon's orbit around the Earth, the planet's motions, and the falling apple could all be explained with this formula. By creating a mathematical language, he transformed observation and experiment into universal law. This approach marked the beginning of an era of mathematical proof in science. Universal gravitation was not just theoretical. Newton demonstrated its applications. He calculated planetary orbits, predicted comet trajectories, and even explained tides using the same law. This was unprecedented in the history of science. A single law applied both in the heavens and on Earth. Newton's work transformed not only the explanation of physical phenomena, but also the scientific method itself. Supporting theory with experiment, expressing it mathematically, and demonstrating its universal applicability became foundational principles of modern science. Prism experiments, calculus, the laws of motion, and universal gravitation. All were links in a chain, and Newton laid this chain before humanity for the ages. From 1672 to 1687, Newton systematically compiled all his work. With the publication of Philosophiae Naturalis Principia Mathematica in 1687, humanity finally possessed a roadmap to understand the universe. The laws of motion and the law of universal gravitation were recognized as undeniable truths, changing the world of science forever. Newton's genius lay not only in discovering the laws, but in presenting them as a mathematical system. When combined with calculus, measurements of motion, optical experiments, and observations, Newton became the first person to understand and explain the universe as a unified whole. This was an intellectual triumph unparalleled in history. It was 1684. Isaac Newton continued his quiet and orderly life in Cambridge. The ideas, calculations, and experiments he had accumulated over the years had now matured, waiting to be presented to humanity. The laws of motion, the law of universal gravitation, the foundations of calculus, optics, and the secrets of light, all were ready to be organized into a coherent system. Yet Newton was a reserved, cautious, and introspective man. He hesitated to publish the monumental knowledge he had developed over years, avoiding disputes in the academic world. He put himself through almost a torturous process to ensure that not a single detail in his work was overlooked. It was during this time that Edmund Halley, a prominent figure in England's scientific community, entered the scene. As an astronomer and mathematician, Halley had already recognized Newton's genius. In 1684, Halley visited Newton and asked, "Why do the planets move in their orbits as they do? Can you explain this motion mathematically?" In response, Newton quickly laid out the foundations of a work that included the laws of motion and universal gravitation. Halley's insistence and support encouraged Newton to finally put his long-pondered ideas into writing. Halley provided both financial and academic support to publish Newton's work. At that time, publishing a scientific book was an enormous financial and logistical undertaking. Without Halley, the birth of Principia would have been far more difficult, perhaps even delayed by years. Newton began his work in 1685. Yet the process was far from easy. He checked every equation, formula, and observation obsessively. Each page was a testament to his brilliance and meticulousness. In some notes, one can see him repeatedly correcting calculation errors and reorganizing equations. He wanted the published work to be flawless. A book explaining the laws of the universe could not contain errors or omissions. In 1687, the first edition of Newton's work was completed and published. Its full title, Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy. The Principia became a turning point not only in the world of mathematics and physics, but also in the intellectual history of humanity. The book was divided into three main sections: laws of motion and principles of dynamics, the motions of Earth and celestial bodies, the order of a universe, and the law of universal gravitation. Halley played a crucial role not only in the publication process, but also in distributing and promoting the book. Scientific circles in London, with Halley's support, paid close attention to Newton's work. When the Principia was published, it caused a stir in the scientific community. Many scholars found the book challenging to understand, yet the universal laws and mathematical consistency were immediately recognized. The impact of the Principia extended far beyond academic circles. Newton's laws of motion and universal gravitation could explain all physical phenomena, from the orbits of celestial bodies to the fall of an apple. Humanity could now understand the workings of the universe systematically and mathematically. Astronomy, mechanics, engineering, and mathematics were all revitalized by Newton's discoveries. The publication of the book elevated Newton to the most respected scientist in all of Europe, not just Cambridge. It brought him international prestige, and many scientists corresponded with him to exchange ideas. Yet, as always, Newton avoided disputes in the spotlight. It was nature itself that spoke through his work. The Principia also became a symbol of the scientific method. By combining observation and experiment with mathematics, Newton sent a clear message to all scientists. The path to understanding nature is through systematic thought. Without Halley's support, this masterpiece might have remained incomplete, and Newton's genius might have remained silent for years. Halley entered history as the unsung hero who ensured that Newton's brilliance reached the world, both scientifically and personally. In summary, the writing and publication of the Principia was the culmination of years of observation, experimentation, and calculation by Newton. Would not have been possible without Halley's encouragement and support, created an immediate revolution in the scientific world, and demonstrated that the universe could be explained mathematically, laid the foundations of modern physics with the laws of motion and universal gravitation. The Principia was the greatest legacy born from the storm of ideas that emerged from Newton's quiet attic room. Through this work, Newton became not only a scientist, but also a historical genius who revealed the mathematical order of the universe. Newton's genius shone brilliantly across the scientific world of England and Europe with the publication of Principia. Yet this brilliance brought with it disputes and conflicts. Newton was a solitary, introverted, and highly sensitive individual. Yet his scientific claims were so powerful that confrontation with other scholars was inevitable. This period became a stage where Newton's intellect was tested and his character was forged. His first major conflict was with Robert Hooke. Hooke was one of the leading figures of the Royal Society in London, conducted his own studies on optics and universal gravitation. Newton had advanced his work on the nature of light and the laws of motion, but when Hooke found these ideas in conflict with his own theories, his criticisms were harsh and dismissive. Hooke claimed rights over Newton's particle theory and law of gravitation, interpreting Newton's findings in a condescending tone. Newton had little tolerance for criticism. For him, scientific truth stood above personal relationships. This marked the beginning of a long-lasting enmity between Newton and Hooke. Even after Hooke's death, Newton sometimes went so far as to remove Hooke entirely from his books and references. Another conflict arose with the astronomer John Flamsteed. Flamsteed was the chief astronomer at the Royal Observatory in England, working on star catalogues. Newton wanted to use Flamsteed's observational data in the calculations for Principia, but Flamsteed accused Newton of using the data incorrectly and incompletely. Their correspondence and disputes continued for many years. Newton, patient and strategic, eventually secured access to Flamsteed's data using his scientific authority. Yet this process revealed the tension between his preference for solitary work and the collaborative nature of the scientific community. Newton's most famous and long-lasting dispute, however, was a calculus controversy with Gottfried Wilhelm Leibniz. Newton had developed his method of flux ions in the 1660s, while Leibniz developed his own version of calculus in the 1670s. Initially, both sides claimed to have worked independently, yet by the early 1700s, the scientific world of England and Europe was divided. Newton claimed that Leibniz had stolen his methods and that he had priority. When the Royal Society intervened to investigate, the dispute became an official academic battle. Newton wrote letters in an extremely sharp and personal tone, fighting to protect both his scientific truth and reputation. This conflict revealed not only his intellectual rigor, but also his ambitious and uncompromising nature. All these disputes shaped Newton's character, introversion, and meticulousness. Newton withdrew from social interactions to protect and present his scientific ideas flawlessly. Long-standing enmities, the conflict with Hooke, Flamsteed, and Leibniz formed a narrative of his academic struggles. Scientific patience and strategy. Newton sometimes waited silently for years, choosing the right moment to defend his discoveries. This period demonstrates that Newton emerged not only as a solitary genius, but also as a competitive and uncompromising scientist. The success of the Principia was reinforced not only by his uncovering the secrets of light and motion, but also by his struggle to preserve scientific reputation and defend his ideas. Newton's letters, his sharp tone in disputes, and his strategic moves made him a legendary figure both in the scientific community and in history. In summary, Newton's scientific debates and rivalries included disagreements with Hooke over optics and gravitation, conflicts with Flamsteed over observational data and astronomy, the priority dispute with Leibniz over calculus, long-standing struggles carried out through letters, official reports, and strategic maneuvers, all of which revealed Newton's solitary genius in both his human and scientific dimensions. Knowing Isaac Newton solely as the father of modern physics and mathematics is to understand only the visible part of his mind. Within the stone walls of Woolsthorpe, in the dim light of the attic where he conducted his experiments, Newton revealed not only the laws of motion in the Principia and his optical studies, but also the more mysterious and hidden sides of his intellect, his alchemical and chemical investigations. Newton's interest in alchemy stretches back to the mid-1660s. At that time, alchemy was considered the precursor to modern chemistry. It was not only the dream of producing gold, but also the effort to understand the transformability of substances in nature and their universal principles. Newton spent hours in his small attic laboratory, working with bottles, furnaces, and mysterious liquids. During his experiments, he studied mercury compounds, acids, and salts. His aim was not merely to observe simple chemical reactions. He sought to understand the fundamental nature of matter and its relationship to universal order. Newton's alchemical notebooks contained far more than ordinary scientific notes. They included quotations from ancient alchemical texts, explanations written in Latin, symbols, and encrypted signs. He kept these works highly secret, sharing them with almost no one. Some historians interpret Newton's alchemical pursuits not as a quest of material wealth, but as a study to unravel the secrets of nature. This aspect reveals a dark yet profound dimension of his scientific curiosity. Newton's interest in alchemy also intertwined with chemistry and experimental methodology. He not only observed the transformation of elements, but also recorded his experiments, questioned the causes of reactions, and analyzed the results systematically. These studies serve as a precursor to the methodical approach found in the Principia: observation, experimentation, and patience. Yet these notebooks were Newton's private and obscure laboratory, invisible to the scientific community. Moreover, Newton's alchemical and chemical notes were connected to his theological and philosophical interests. He related the transformation of matter and universal principles to the workings of a universe created by God. In Newton's mind, alchemy was not just about producing gold or laboratory experiments, but about deciphering the hidden order of the cosmos and understanding God's plan. Therefore, while his alchemical experiments might appear as occult science in the modern sense, for Newton, they were integrated with universal logic and mathematical order. Another dimension of Newton's alchemical and secret chemical work was his system of recording and encrypting information. Most of his notes were written in Latin, filled with symbols, and rendered deliberately difficult to interpret. This served both to protect the knowledge and to create a system that only he could understand. Today, historians study Newton's alchemical notebooks to understand how he attempted to bridge the boundaries between chemistry and physics in his laboratory experiments. In summary, Newton's alchemical and secret chemical studies reveal a lesser-known yet profound dimension of his scientific curiosity, represent an effort to understand the fundamental nature of matter and the universal order, demonstrate his habit of systematically recording experiments and observations, are integrated with theological and philosophical context, can be seen as an early precursor to modern chemistry and scientific methodology. These dark studies of Newton show that he was a genius, not only living by logic and mathematics, but also driven by the desire to unravel the universe's mysteries. Beyond the clear and visible achievements in the Principia, Newton's mind embarked on a deep journey from an attic laboratory toward the most hidden secrets of nature. Isaac Newton's genius was not confined solely to mathematics, physics, and optics, as he sought to understand the order of the universe. He was also deeply engaged with the existence of God and the divine order. Throughout his life, science and religion were inseparable for Newton. The quiet stone walls of Woolsthorpe and his attic room were not only the place for prisms and formulas, but also for sacred texts and theological inquiry. Newton's theological studies primarily focused on biblical interpretations and the analysis of prophecies. His interest was less about dogmatic beliefs and more about understanding the text in a historical and mathematical manner. Newton sought to decipher the prophecies in the Bible, especially the timelines in the books of Daniel and Revelation, through mathematical logic. By comparing historical events with sacred texts, he attempted to comprehend the unfolding of God's plan. These studies were often as meticulous as his laboratory experiments. Each verse and historical reference was carefully examined and analyzed. Newton's theological interest also extended to the doctrine of the Trinity and the historical roots of Christian teachings. He critically examined some of the dogmas accepted by the Church, particularly pondering the Trinity and tracing its historical origins. His research offered more personal and profound theological perspective, distinct from mainstream Christianity. Newton's faith was less about dogma and more about understanding the order of the universe and God's will. Newton's theological pursuits were also intertwined with alchemy and natural philosophy. For him, the mathematical order of the universe and the laws of physics were evidence of God's existence and providence. Laws of motion, universal gravitation, and optical experiments were not merely physical truths, but visible proof of the divine plan. Thus, Newton's scientific and theological endeavors progressed as complementary domains. Newton's theological notes and manuscripts provide modern scholars with significant insights into his belief system. Across thousands of pages, he analyzed the chronology of sacred texts, the timelines of prophecies, and the logic of the divine plan. He did not share these studies with the public, but recorded them for his own understanding and meditation. This aspect of Newton makes him unique, both as a pioneer of modern science and as a profound theological thinker. Newton's theological work demonstrates that he sought to comprehend not only the physical world, but also the metaphysical and divine order. While he is renowned for the Principia and his optical experiments, the hours he spent in quiet contemplation with sacred texts in his attic reveal another facet of his genius. A thinker standing at the intersection of science and faith. Isaac Newton's life stands out not only for his scientific genius, but also for the complexity and nuance of his personal character. From the stone house in Woolsthorpe to the academic environment of Cambridge, Newton was mostly known for his solitude and introversion. His personality was shaped by his keen observational skills, meticulousness, and sensitivity, directing his focus far more toward intellectual endeavors than social interactions. Newton's immediate circle was very limited. His family, particularly his relationship with his mother and stepfather, formed a complex dynamic during his childhood and adolescence. His mother, Hannah, had become a widow before Newton's birth and played a significant role in raising him. This early experience of being largely on his own reinforced Newton's habit of retreating into his inner world. His friendships were typically brief and selective. He avoided forming close bonds with those he did not trust. This solitude became both the wellspring of his creative thinking and scientific brilliance, while simultaneously deepening his social isolation. One of the most prominent aspects of Newton's character was his meticulous attention to detail. He would not tolerate the smallest mistake in his experiments, calculations, or writings. This precision earned him respect in the scientific world, but also complicated his personal relationships. At times, he appeared cold or harsh to friends and colleagues. However, underlying his behavior was an intolerance for error and a drive for perfection. Combined with his stern demeanor in scientific debates, Newton emerged as a solitary yet immensely effective academic figure. Certain personal habits and lifestyle choices further highlight his uniqueness. Newton would spend long hours in his laboratory, turning night into day, sometimes forgetting to eat in the midst of research. Sleeplessness and working alone were routine for him. This solitude was both a source of creativity and a factor limiting his social life. Newton maintained social interactions with the public or academic circles only when necessary. Otherwise, he preferred to retreat into his own world. Among his relationships, limited closeness can be observed with some of his students and select colleagues. Supporters like Edmund Halley played a critical role in helping Newton publish his work and recognize his talent. Yet Newton remained emotionally distant even from these individuals, maintaining a reserved stance when sharing his ideas. Newton's solitude and the nuances of his character were directly linked to his scientific brilliance. While he left humanity an unparalleled legacy with the Principia, the laws of motion, universal gravitation, and his optical studies, he lived as a solitary, intensely contemplative mind. Newton's story represents a balance between genius and solitude, meticulousness and inner struggle, rendering him not only a remarkable scientist, but also a fascinating study of human psychology. The final years of Isaac Newton's life were marked by the indisputable recognition of his scientific genius. Crowned with fame and prestige, his achievements through Principia and optics had made him a respected figure not only in Cambridge but throughout Europe. His influence in the Royal Society, his weight in the scientific world, and his authority as a thinker made him one of the most impactful intellectuals of his era. In 1696, Newton stepped outside the purely scientific realm when he was appointed Master of the Mint at the Royal Mint. This position provided him not only with financial security, but also the opportunity to play a significant role in England's economic policies. Newton carried out his duties with meticulous precision, combating counterfeiting, maintaining currency standards, and implementing financial reforms, all with extraordinary discipline. His logical mind and careful calculations were decisive in the success of anti-counterfeiting operations. This aspect of his life stands as a unique example of applying scientific methodology to social and economic fields. By 1705, Newton's fame in England had reached its peak when Queen had knighted him. Sir Isaac Newton had now become not only a symbol of the scientific world, but also of England's national prestige. This honor acknowledged his disciplined and meticulous life, as well as his scientific and societal contributions. The knighthood made him publicly recognized, yet his innate introversion and humility allowed him to carry the title without concern for personal fame. However, these years were also marked by health challenges. Years of intense work, sleepless nights, and solitary hours had taken a toll on his physical well-being. As he aged, he occasionally faced digestive issues, headaches, and general fatigue. Nevertheless, his mental capacity and scientific productivity remained impressive even in later years. Newton never abandoned science. His thoughts and notes continued systematically until shortly before his death. Isaac Newton passed away on March 31st, 1727, in London. His death was a significant loss to both the scientific community and British society. His funeral was conducted with grandeur and reverence. The ceremony at Westminster Abbey immortalized him not merely as a scientist, but as one of England's greatest intellectuals and a national icon. The event was also a collective expression of respect from the scientific world toward a true genius. Newton's legacy was not limited to books, articles, or theories. The laws of motion and universal gravitation laid the foundation of modern physics. Calculus accelerated the evolution of mathematical thought, and optics opened the path for modern optics. His systematic approach, combining observation, experimentation, and mathematics, became a model for future generations of scientists. His alchemical and theological studies painted an extraordinary intellectual portrait, merging science and metaphysics. The final years of Newton's life represent the pinnacle of both his scientific genius and character. With his passing, not only an era but also one of the most remarkable scientific minds in human history came to a close. His legacy continues to live on eternally in the form of universal laws, methodical thought, and intellectual contributions that illuminate humanity. After his life, Isaac Newton left behind a legacy that profoundly influenced not only his era, but all of human history. Through the laws of motion, universal gravitation, calculus, and optical studies, he laid the foundational stones of modern science. His scientific approach, combining systematic observation, experimentation, and mathematical reasoning to understand nature, was passed down to future generations. Newton's method served as a guide for scientists. Answers arise from observation and logic, not speculation. Newton's legacy extended beyond theoretical contributions. Works like the Principia and Optics remain core texts in scientific education for centuries. By mathematically framing the ideas of Galileo and Kepler, Newton's scientific method and universal laws became indispensable for subsequent physicists, mathematicians, and engineers. Revolutionary ideas, such as Albert Einstein's theory of relativity, were even built upon Newton's understanding of universal gravitation and motion. Newton's name became legendary in the history of physics and mathematics. His tomb at Westminster Abbey in London remains a symbol of his contributions to science and humanity. Cambridge University and many other institutions have honored his work with monuments, statues, and museums. His portraits, laboratories, and notes are still preserved as central elements in the history and teaching of science. His legacy is not confined to pages, laws, or books. The discipline and method he brought to scientific thought guided generations in humanity's quest to understand the universe. By expanding the boundaries of mathematics and physics, Newton demonstrated that the pursuit of knowledge and curiosity represents one of the highest expressions of human intellect. And so, dear listeners, we have shared with you the life, genius, solitude, struggles, and legacy of Isaac Newton. His story is a beacon not only for the scientific world, but for human history itself, a testament to curiosity, determination, and discipline. Thank you for joining us on this journey. We hope that Newton's universal wisdom and the unique contributions he made to humanity have inspired you as well. Keep exploring, keep questioning, and continue your pursuit of knowledge.